So we talked about minerals being one of the things that are transported through plants. So mineral elements are used in building plant tissue, organs, and various chemical constituents of plants. Macronutrients are used in the greatest quantity. Micronutrients are used in much smaller amounts, but are also very important. So of the macronutrients, we've got carbon, atmospheric element. It's used in photosynthesis in tissues. Hydrogen is derived from water. It's used in photosynthesis. Oxygen is an atmospheric element used in respiration. Nitrogen is a geologic and atmospheric element important for chlorophyll synthesis. This is one of our primary macronutrients. Phosphorus is a geologic element, also a primary macronutrient used in cell and DNA building. Potassium is a geologic element used in enzyme synthesis, also one of the primary macronutrients. Calcium is a secondary macronutrient, which is a geologic element, but important for membrane development. Sulfur is a geologic element, also a secondary macronutrient. Protein synthesis is one of the things it does. So here's just some pictures of some deficiencies, and with nitrogen and phosphorus, they are mobile nutrients. So you're going to see these yellowing leaves for nitrogen and purpling leaves for phosphorus deficiencies in the lower leaves, while the newer growth will be green. Here's magnesium deficiency, and then we've got potassium deficiency, also a mobile nutrient. You're going to see this damage in the lower foliage. Here's some more potassium deficiency. It starts as a marginal burn and then just moves its way into the leaf. Sulfur deficiency, this is going to be an immobile nutrient, so it's going to stay in the lower portions of the plant and not get to the newer growth, so you're going to see this yellowing. Here are some calcium and boron deficiencies, and on the left upper corner you see a watermelon here that's got blossom end rot, which you may be familiar with for tomatoes and peppers. And the reason this happens is because calcium is not plentiful and the membranes are not developing properly, so the membranes collapse and then fungi move in and take advantage of the situation. Okay, iron chlorosis is the deficiency of iron, and it's really a lack of access to the iron. So rhododendrons, camellias, azaleas, blueberries are all acid-loving plants, and the reason they are acid-loving is because iron is more available to them in more acidic soils. Once they start getting up around neutral in pH, they will get this kind of damage, and it's an immobile nutrient, so it's going to be the new growth that shows up this way. And here on the right we have zinc and manganese, zinc being on the left and then manganese on the right. And just to be familiar, we won't get too much into this, but there are several nutrient cycles involved in providing nutrients for plants, and one of them being the nitrogen cycle. Of course, there's the carbon cycle, potassium or phosphorus cycle, etc. Okay, sources of elements include organic, which are derived from living organisms and or naturally occurring minerals. There's lower concentrations, so they're more slowly released and quite often need to have microorganisms to aid in this release. Inorganic are synthesized or manufactured, and there's custom concentrations and formulas with various variable release rates. Usually you'll see this on the fertilizer. If it's a fast release, it's going to have higher numbers. So commercial fertilizers have formulas expressing their macronutrient contents as a percentage of their bulk, and by law they have to have nitrogen, phosphorus, and potassium on the label. And so these are just percentages. So this is 20% nitrogen, 10% phosphorus, 10% potassium, and 20 is a pretty high number, so that's going to be a pretty fast release fertilizer. When you're trying to use an organic fertilizer, you would want to use something with a nitrogen of like 3%, because it's going to be much slower, but it's going to be much safer for the environment. So soil is an aggregation of geologic and organic materials. The geologic materials are sand, silt, and clay, and then organic materials are humus. And this is our ideal soil. So 50% of soil should be pore space, and hopefully that's broken in half by air and water. 45% would be mineral, so that'd be the sand, silt, and clay, and then 5% would be organic matter. This is idealized, usually not the case. So soil properties are looked at with texture, coarse or fine. That will govern the pore space. So smaller pore spaces are very good for water retention, or bad, depending on what you're trying to do. And large pore spaces are good for aeration. And I was just mentioning acidic soils and availability of nutrients. So you may have heard that a good pH for plant growth would be 6.5. And if you look at 6.5 and up to 7, you'll see that the bands of the nutrients are fairly broad all the way down. That means those nutrients are available to the plants. If you look down at iron, you can see it gets broader as the soil becomes more acidic. So that's what I was mentioning. If your soil pH is too high, you will get an iron deficiency for your acidic loving plants. Okay, soil texture is determined by the amounts of sand, silt, and clay. This excludes organic matter and some of the larger particles. And sand is the largest mineral particle, followed by silt, and then clay. So here's the relative size of the soil particles. Sand is pretty large compared to silt, and that's pretty large compared to clay, and that's that little square on with the arrow pointing at it. So particle surfaces are important. They might be coated with water. They could be electrically charged. There should be sites for microbial growth. There are also sites of chemical reactions that happen with weathering. Adsorption of chemicals, that's just the adsorption means that it's attaching itself to the soil. Retention of nutrients and soil aggregate formation, which is really important for good drainage and actually much healthier for root growth. So clay particles have an electrical charge, some more than others, and we'll get into that in soils. Most clay particles are negatively charged. Ions are charged molecules, and cations are positively charged ions. So cations are going to be attracted to the negatively charged clay particles. Anions are negatively charged, so they're not going to be attracted to those negatively charged clay particles. So, as I said, cations are attracted to negatively charged clays. They're either loosely held or exchangeable. And that's called cation exchange. So here's just a picture of a clay particle with all of these cations floating around, and they should attach themselves to the clay particle. So exchangeable cations include calcium, magnesium, potassium, ammonium, and sodium, and if in acidic soil, hydrogen and aluminum are included here. Exchangeable cations can replace one another. Exchangeable cations are available to plants, microbes, etc. And the amount of exchange in a soil is called cation exchange capacity.